we are starting a new topic called chromatography. Chromatography is the most important in bioprocess downstream operations because it is very well suited for biomolecules like proteins, enzymes and those which are very temperature sensitive, whereas in chemical engineering downstream processes they use distillation as a purification technique, whereas here we cannot use distillation as a technique because of the temperature sensitivity nature of the biomolecules. So, chromatography is very extremely efficient and there are different types of chromatography operating on different principles, and that is what we are going to spend some time on. And we will be spending almost 4 classes on chromatography because it is a very involved topic. So, it is used for separation of proteins, especially in biopharmaceutical industries, for medicines. It is used for isolating pure enzymes. So, it is widely used. For example, nucleic acids, carbohydrates, fats, vitamins, even small molecules can be separated using chromatography, and there are different types of chromatography like I said: ion exchange chromatography, size exclusion chromatography, and then reverse phase chromatography and so on actually. So, we will talk about each one of them and we will also look at some problems involved in chromatography. So, where do you use it? It can be used for separation, purification, it can be used for identification of compounds also. As you know, you must have all heard about HPLC, right, high pressure liquid chromatography, high performance liquid chromatography. So, generally HPLC is used for analytical purposes, for identifying unknown molecules, for finding out the concentration of unknown molecules in a mixture. So, it has become very useful, the HPLC. So, we will look at that also. So, in chromatography the selective distribution of components from a mixture between 2 phases, you may have a stationary phase, you may have a mobile phase. As the name implies, stationary phase is a solid and mobile phase is a liquid or sometimes it is a gas. Okay. So, one is called the stationary or solid or immobilized liquid. So, you can have pure solid alone or you can have a liquid immobilized on that. The other one is a mobile phase, it could be a gas or it could be a liquid, okay, and mixtures of gases and so on actually. So, what do we do? You have a long column and the stationary phase is packed inside this long column and a mixture is injected from one end. Okay, it will be generally a very sharp peak, and then as it travels through it and the solute gets partitioned, solute gets adsorbed on the surface, solute starts interacting with the stationary phase material. So, many things can happen, different types of non-bonded interactions happening between the solute molecule in the liquid phase and on the solid phase. So, slowly they start spreading out, okay, and finally when it comes out like a Gaussian peak or it comes out like a normal distribution at the end of it. So, if there are many solutes traveling through it, you will get many peaks corresponding it, each one may be overlapping with one another, but basically when you inject a very sharp peak, it comes out like a normal distribution. Why does it happen? It happens because of the interaction between the solute with the stationary phase and partitioning of the solute between the stationary and the mobile phase and so on. Because of that the age distribution of this solute varies, okay, and that is called dispersion. So, the shape of the curve is generally assumed to be normal and the height and the width makes a lot of difference, and from those parameters we can tell how efficient is your separation process and so on. So, we will look at some problems related to the height of these normal distribution curve as well as the width. So, we have a mixture of solutes here and there is a solvent, or sometimes if it is gas there will be a gas, carrier gas here. So, the proteins get separated like this, and as it travels and travels they get separated one after the another after the other, and that is what happens in a chromatographic system. Okay. So, as the time increases slowly they get separated more and more, and as they travel they get separated out. So, the concentration of any one solute varies as a function of length as well as a function of time as well. Okay. Now, if you look at you must have heard about gas chromatograph. Gas chromatograph have been there for a very long time. So, if this mixture of solutes are vaporizable, then gas chromatograph is also a very cheap and a very powerful technique. So, the mobile phase there is a gas. Okay. So, the solid phase or the stationary phase could be a solid, completely solid, or a liquid which is immobilized on a solid phase. Okay. So, this is a gas chromatograph. And then you have different types of mobile phase, gas or liquid and so on actually, and the solid the stationary phase could be just the solid, or it is a liquid immobilized on solid, or plain solid. Okay. So, you have the gas solid chromatograph, gas liquid chromatograph and so on actually, paper chromatograph, thin layer chromatograph. So, a lot of different types of chromatographs are there, each one making use of different physical principle. Okay. So, you must have heard about thin layer chromatograph. We all use thin layer chromatograph in our regular chemistry experiment, where you want to identify some components. This is a very simple technique and very extremely powerful and very cheap also. Then we have the gas liquid chromatograph, liquid solid chromatograph, paper chromatograph, liquid liquid chromatograph, gas solid chromatograph, bonded phase chromatograph. So, different types of chromatographs are there actually. These are based on column. So, you have a column in which your stationary phase is packed, whereas these are based on planar or paper. For example, paper chromatograph and thin layer chromatograph, they are planar. So, the solute and the solvent travels over a thin planar paper. Okay. So, what is the physical principle? If you look at gas liquid chromatograph, the volatility of the various components present in the mixture, that is the principle. If you look at liquid chromatograph, we are looking at partition coefficient. That means the partition coefficient of the solute in the stationary liquid vis-a-vis the mobile liquid. Okay. That is what it is. Same thing if you look at liquid solid chromatograph, again partition coefficient come into picture. If you look at ion exchange chromatograph, charge on the molecules, could be a biomolecule or it could be a protein. So, the charge determines the separation process. If you look at hydrophobic interaction chromatograph, the hydrophobicity, as you know, proteins, different proteins will have different extent of hydrophobicity, and this particular chromatograph makes use of that principle for separating out proteins. This is also called reverse phase chromatograph or interaction chromatograph. Okay. Then gel permeation chromatograph or size exclusion chromatograph, they are based on diffusion, size of the molecules. Okay. Smaller the size or bigger the size, they get separated. So, this is basically based on sizes. Then we have the affinity chromatograph, it sort of recognizes the molecular ligand protein interaction. So, you may have a ligand immobilized on a stationary phase. So, proteins which exactly bind to that ligand only are bound, whereas other proteins are washed out. So, we can specifically extract proteins which are very selective for that ligand. So, this is a very powerful technique for separating out a single protein from a large mixture. Okay. So, like antibody antigen separation, ligand protein exactly. We will look at each one of them little bit in more detail later. So, basically this is how it will look like. You may have the carrier gas or carrier solvent or the mobile phase, okay, and then you have a pump. The pump injects the mobile phase through this column, and then you may inject the sample here, okay, and then the material travels through that, and then each one of them come out. There is a detector here, and then here you have the collector here. Okay, the detector will tell you which peak is coming out. So, we can collect the products on different collectors, that is why it is called fraction collector. So, typically any chromatographic setup will have this type of assembly. Okay. So, the most important parameter that is called partition coefficient, that is the concentration of solute in each phase. We have seen partition coefficient in, where have you seen? We have seen it in liquid extraction, that is the partition coefficient, right. So, same thing comes here, K, the partition coefficient, okay, that is the concentration of solute in the stationary phase and in the mobile phase concentration. Okay. See, ideally partition coefficient is a constant over a range of concentration. So, irrespective of concentration, partition coefficient should be constant actually. Okay. If the value of K determines the average velocity of each solute. Okay. So, if K is very large, what happens? The solute gets more absorbed, I mean more partition onto the stationary phase, so it travels very slowly. Okay. K is equal to 1, that means solute is equally distributed in 2 phases, then that is not a good continuous phase material, because you will not achieve any separation. If 2 components in a mixture have Ka equal to Kb, then the separation factor is 1, so no separation. Okay. If Kb is greater than Ka, then what happens? Kb travels slowly on the stationary phase, Ka travels faster on the continuous phase, so A elutes out first. Okay. If Kb and Ka are equal, both will get partitioned at the same ratio onto the stationary phase, so you will not get any separation at all. Okay. Okay. So, if you look at liquid partition chromatography, so we have the stationary phase and then there is a stationary liquid coating on top of it. The solvent comes, that is the continuous phase, so the solute partition. So, this is exactly like extraction, only thing is one liquid is immobilized on the surface, this is exactly like extraction. So, you will have the term partition coefficient coming into this picture, especially for liquid partition chromatography. So, stationary phase is will have a solid matrix here and a liquid that is coated onto the stationary phase. Okay. So, this is exactly like liquid extraction, only thing is one of the liquid is immobilized on the surface. So, typically as I said, the solute will come out in this fashion. We will call this a normal distribution or uniform distribution or Gaussian distribution and so on. Okay. So, this is the x axis could be time. So, I am injecting it at time equal to 0. Okay. So, at time equal to some time, we call it the elution time T naught, it will come out the maximum, that could be C naught. Okay. So, but generally you will not get this type of graph, there could be some skewed either tail or fronting and so on can be happening. Many times it will not be like a normal distribution like a bell curve, the shape may be different. There is something called the retention time, like I said, this is the retention time. Okay, the time it takes for the liquid peak to achieve that maximum here, that is called the retention time. Okay, the retention time depends on the flow rate F of the mobile phase. So, F is equal to volume into P, that is the porosity of the stationary phase divided by Tm. Okay. So, that means Tm will be Vp divided by F, P is the porosity, Tm is the time required for a molecule of the mobile phase to pass through the column. Okay, there is something called corrected retention time, because as soon as you inject there will be some peak coming out. Okay. Okay, that is called the Tm. So, if you get a retention time, okay, we need to generally subtract this time with this time, okay, to get the actual retention time. Okay. So, we need to subtract. So, if you have many components, then the output may look like this. Okay. We can say that component 3 is separating out very well because it is clear, when the baseline is very clear, whereas in this particular case component 1 and component 2 are not separating very clear, you can see a overlap here. So, if I am collecting component 2 at this time, you could get component 1 also, maybe after this you may get only component 2, but here you may get component 1 and 2. So, that problem is always there, whereas here with respect to component 3 there is no contamination from either 1 or 2. So, ideally you would like to have a peak of this shape and size, whereas you would not like to have like this, where two of the peaks are overlapping with each other. So, the retention time of a solute is affected by the nature of stationary phase, that means what type of stationary phase I am using, what is the particle size of the stationary solid, what is the porosity and so on. Composition of the mobile phase, am I using a hydrophilic mobile phase, I am using a hydrophobic, I am using a mixture of them, what is the dielectric constant and so on. Then column dimension, what is the length of the column, what is the diameter of the column. Okay. Then mobile phase flow rate, how fast or how slow the mobile phase is flowing through. So, all these affects the retention time. I am not talking anything about the separation efficiency, but I am just talking about the retention time. That means what time it will take for a particular solute to come out. For a given stationary and mobile phase composition, the retention time of solute increases with the increase in length of the column, it is obvious. So, if I have a very long column, it will take much longer for the stationary phase to come out, obvious, with decreasing flow rate of mobile phase. So, if I decrease flow rate, then it will take much longer time. So, if I increase length also it will take much longer time, if I decrease flow rate also it will take much longer time. I am not please note I am not talking about the separation efficiency, but I am talking only about the retention time. If I have two components, then both the components will also feel the same. If I reduce the flow rate, both the components will come slower. If I increase the length, both the components will come out slower. Okay. Now, similar to retention time, you also have retention volume. So, retention volume is given by retention time into flow rate, it is obvious, right. So, that is the volume of the mobile phase required to transport that solute from start injection point right up to the detector point end, right. So, that similarly, if you want to do corrected retention volume, we need to subtract with respect to Vm, like if you remember I mentioned something called Tm here, right, because if you just inject, you will get a small peak corresponding to the dead volume of your pipe packed material. So, actual retention time, if you want to correct it, you need to subtract this retention time with this Tr. Similarly, if you want to know the actual retention volume, you may have to subtract with respect to Vm. Okay. So, Vm is the column dead space or void volume, as you can see, okay. Remember that. So, Vm is the column dead space or the void volume. So, there is something called capacity factor and retention ratio. Let us look at this. What is the capacity factor? It is a measure of the retention of a solute component, how much of the solute can be taken in that particular column. So, it measures time spent by a solute in the stationary phase related to time spent in the mobile phase. Okay. This is called something to do with the partition ratio, right, because mobile phase and stationary phase, if you are looking at ratios, then partition coefficient also comes into picture, or it is coming as mass distribution ratio also. So, it is the total amount of solute present in the stationary phase to that in the mobile phase. So, obviously, so if Vs is the volume of the stationary phase, Vm is volume of the mobile phase inside that column, Cs is the concentration of the solute in the stationary phase, Cm is the concentration of the stationary phase in the mobile phase, then K dash is equal to Cs Vs. This gives you total amount of solute in the stationary phase inside the column, total amount of solute in the mobile phase inside that packed column. That ratio is called capacity factor. Okay. Then we have something called column efficiency. Now, we come to the efficiency of separation. Okay. So far we looked at retention time, all those things, but then when we have many peaks, ideally I would like to have a good separation between two peaks. That is what I want. Ultimately, in a chromatography I want to achieve that. So, column efficiency of the separation, it is related to the width of the chromatographic peak. If the width of the chromatographic peak is large, if I have two peaks and both of them are very large, then they will be overlapping on one another. So, obviously the column efficiency is very poor. If the width of the peak is very small or very sharp, then you may have a good column separation, that means good column efficiency. There is a term called theoretical plate, okay. This comes from chemical engineering. There is a term called theoretical plate, okay, number of theoretical plates. So, a column is divided as consisting of lot of theoretical plates, and separation is taking place in each theoretical plate, okay. So, more the number of theoretical plates, better is the efficiency expected. So, each column, it can be converted to certain number, that is called the number of theoretical plates, okay. So, if then corresponding to theoretical plates, we also have another term, that is called height equivalent to a theoretical plate. So, ideally if I have a very small height equivalent, then I can say it is a very good efficient column. So, if I have very large number of theoretical plates, then I can say it is a very good column with good efficiency. If the height equivalent of a theoretical plate is very small, then I would say the column is very good and it can do a good separation. So, two terms, these two terms comes from chemical engineering, mostly from distillation column. So, if you have large number of theoretical plates, then you can say the column is very efficient. If you have a very small height equivalent of theoretical plate, then you can say you have a efficient column, okay. How do we calculate number of theoretical plates? We will come to that as we go along. There is a formula for height equivalent of a theoretical plate. H, height equivalent of a theoretical plate, is given by sigma square by L. L is the length of the column and sigma square is the variance. As you know, the spread, variance is the spread of the normal distribution curve which we are talking about. So, good H values for a 90 micron bead is between 0.018 and 0.027 centimeter, and good H value for a 34 micron matrix is between 0.007 and 0.01 centimeter. So, these are some figures, experience based figures. Again they are come from engineering, because in chemical engineering you have distillation column, packed distillation columns, where you have packing of beads of different sizes. So, these terms come from there. So, H is given like this, H is equal to sigma square by L. H is called the height equivalent of a theoretical plate. So, smaller the H, suppose if I am comparing two columns and H of one column is lower than H of another column, then I can say that particular column is more efficient than the other column. If I have two columns and if the number of theoretical plates of one column is higher than that of other, I can say that column has better separating efficiency. How to calculate number of theoretical plates? We will come to that soon. Okay, so, you have as I said, a peak like this coming out as you inject at time equal to 0. Okay, this x axis could be time, retention time, or it could be retention volume. Like I said, retention volume is nothing but retention time into flow rate. Okay. This is called the width at the base. How do you estimate? You draw a line, a tangent at the maximum place, okay. Steepest portion, you draw another tangent and you take this. This is called the width at the base. This is called the height, okay. This is called half width. Half width is half of the height. Now, if you have h here, you take half h, this is the half height, okay. Now, there are some correspondence at half width, base width, this is called base width and this is called half width. So, there are some relationships which connect these numbers with theoretical plates, efficiencies and so on. So, we will look at it actually. So, you understand. So, as the separation happens when you inject at time equal to 0 and at the retention time or retention volume, you get a peak of this form. You draw a tangent, okay, at the maximum inflection point, you draw another tangent at the maximum inflection point, and you look at the base, that is the width at the base. and then this is the height, and half height, if you measure the width, that is called half width. Okay. There are some relationships, as I said, connecting these with the efficiency of your column, because as I originally said, if the separation efficiency is good, the width will be smaller. So, there will be an inverse relation between efficiency of separation and the width, because width indicates spread, spread indicates inefficiency. Okay. Okay. So, as I said, this is a normal distribution, these pictures. So, just to recap, if you remember, you must have studied long time back, this is the equation for a normal distribution, some number a exponent x minus b by 2 c square, right, x minus b, x could be, b could be the average value, right, if you remember long time back, and c is called the standard deviation, okay, if you remember. So, similar equation we could derive for the change in the concentration as a function of time for the Gaussian peak that is coming out of a chromatography column, same. So, it will be of this form, C is equal to C0 exponent T minus T naught minus 1 divided by 2 sigma square. T naught is your retention time. Okay. So, T naught sigma is equivalent to your standard deviation. So, T naught sigma is the standard deviation of the peak, and T naught is equivalent to your mean, or that means the constant the time at which the peak is maximum, or it is the retention time, correct. Similarly, we can get another equation, just like retention time we can get for retention volume. So, that is the volume required to elute the maximum concentration. So, similar. So, here standard deviation will be V naught into T, sorry, V naught into sigma, just like T naught into sigma. Okay. So, because I am comparing with the Gaussian equation, this you must have already studied long time back in your statistics and so on, normal distribution or Gaussian distribution. So, if you compare that, we will get this as T naught sigma as the standard deviation, or V naught sigma as the standard deviation. Okay. So, that is how the equations, that is how the concentration varies with time here, and this is how the volume varies with time. Okay. T naught is your retention time, V naught is the retention volume. Okay. Okay. So, we have an equation. This equation is very useful, we can do many things with this equation, and we will do some problems later on actually. Okay. So, so I have a curve like this going up. So, if I want to know amount of I, a solute, I solute eluted in this time period, that means between T and T naught. So, what do? I do an integration of that, right, C into Q, Q is your flow rate, concentration into Q into dt. For the C, I have an equation in the previous page which I showed you, right, as a function of T naught and sigma and so on. If I want to know the total I, then I need to integrate between 0 and infinity. Okay. So, that is why I have 0 and infinity. But if you want to know how much between these two times, I will integrate between T and T naught, T dash. So, if I collect a sample between this time to this time, I will get only this much amount. If I collect the same sample from 0 to infinity, I will collect the entire solute amount, but then I could be having impurities also as I go along. So, generally we collect when the peak is rising and in between the rising and the falling, right. So, we will not be collecting the entire solute I, but you may be collecting only when it is showing maximum concentration. So, you will be losing the solute in this period of time or in this period of time also, right. So, the efficiency of collection depends upon the time, minimum time and maximum time within which I am collecting these two for the solute, and that is given by this. So, we could integrate this equation. If you remember, this is the C naught C equation, I could put there, I could integrate and I'll end up with a slightly complicated looking equation. We will look at it later on, and if I can integrate between T dash to T, or I can integrate between 0 to infinity and so on actually. Okay. So, we will look at it after some time. So, the process that occurred during the movement of the sample through the chromatographic column, so many things happen. The solute is transferred from the bulk solution to the surface, from the surface it diffuses into the packing, it interacts reversibly with the packing. So, it could be absorption, it could be interaction, non-bonded interaction, so many things. Okay. Then it gets desorbed, diffuses out from the packing, and then it goes back into the bulk solution. So, it is moving from the bulk to the surface, and then it moves and goes to the surface of the packing material or the stationary phase. Then it could be getting desorbed from the packing onto the from away from the surface, then it could be moving into the bulk. So, all these are retarding your solute passage. So, it becomes slower and slower. So, the more it comes slower, the retention time is longer. So, each of the solutes have different retention times, that is why the partitioning of this material takes place. Okay. So, with that we will stop on chromatography, and we will continue in the next session further. And as I said, there are many types of chromatography, and we will look at each one of them as we go along. Thank you very much.